Becoming comfortable with drawing organic compounds and the different ways we represent them with different types of structures can be pretty daunting. One of the things that can really help with choosing correctly drawn structures is identifying that there's really only a certain number of combinations. If you have carbon, oxygen, nitrogen, hydrogens, and halogens, there's an unlimited number of ways that you could put those atoms together to build different types of structures and isomers. Turns out, however, that there's only a select combination that really occur frequently. So I want to go through and talk about half a dozen, 7 or 8 of the common functional groups and really kind of point out the patterns. And hopefully you can see this type of organization and classification can help you determine how to draw many of the possible types of structures. I'm going to start with a compound everybody's familiar with, and that is water. It turns out water is a good example, good starting place, because we have some compounds that have a structure very similar to water that are very common. I'm going to take off one of the hydrogens and put a carbon chain. And I'm going to start with the simplest carbon chain. In this case, it's a methyl group. This particular compound is called methanol. These are alcohols. Alcohols are defined by having an oxygen with a hydrogen on one side, an alkyl group on the other side. This alkyl group could be any number of carbon chains. And in fact, we often are going to represent alcohols generically just by putting the letter R. And R just represents a generic alkyl chain. Now there's some very important properties that you'll want to associate with alcohols. We have a lot of hydrogen bonding, so they have high molecular weights, high boiling points. They're both acidic and basic, just like water is. And so alcohols are also very common solvents and very common compounds in nature. We're going to continue this, so if you can kind of think about this going from water to an alcohol, we're now going to go from an alcohol. I'm going to take that hydrogen that's on the other side, and I'm now going to replace that with another alkyl chain. And these are called ethers. Turns out the ethers look very structurally similar to our alcohols, but they have very different chemical reactivity. Taking this hydrogen off really changes acid-base nature of the molecule. There's very little intermolecular bonding compared to the hydrogen bonding in an alcohol. So these have low boiling points, low melting points, and they're not very reactive. Our ethers are often used as solvents because they don't react with a lot of other compounds. A generic way to represent an ether is to just write R's, and the alkyl chains can be the same or they can be different. If they're the same, you have methyl groups on each side, it's symmetrical. If you have a different carbon chain on each side, then it's an unsymmetrical ether. Both of them are very common. So that's 2 of our most common functional groups. I now want to just modify this a little bit and start with a compound that a lot of people are familiar with, and this is formaldehyde. Notice I've changed this a little bit from our water molecule. I've included a carbon-oxygen double bond with hydrogens on both sides of the carbon. Now this would be considered our most simplest carbon-oxygen double bond molecule. We don't do a lot with formaldehyde. This carbon here is sp2 hybridized. The whole molecule itself is trigonoplanar in shape. But what I'm going to do is take one of these hydrogens off, just like I did with water, and put a carbon chain on. And again, I really can put any carbon chain, and we could go ahead and write that as an R group there. This is now called an aldehyde. Aldehydes are classified as having this carbon-oxygen double bond here, And on one side there's a hydrogen, on the other side there's an alkyl chain. And again, that alkyl chain can be a long carbon chain, it can be a short carbon chain, it can be an aromatic group. That doesn't change the nature of the functional group. So this is a very common pattern. Let's do the same thing that we did with our ketones. And we're going to continue this. I'm going to take the hydrogen off the one side. I'm going to put another alkyl chain. Now this is compounds called acetone, very common solvent that we use. This is called a ketone. And we can represent that generically just by putting R groups. Again, ketones, just like ethers, can have the same alkyl chain on either side, or they can have different alkyl chains. Ketones and aldehydes react very similar. Aldehydes are a little more reactive. We'll see slight differences between the two when we start talking about reactivity of carbonyls, but we classify them together because they are very similar. Building upon our carbonyls, our ketones and aldehydes, I'm going to continue looking at functional groups that have a carbon-oxygen double bond. But instead of having a hydrogen or a carbon now continuing our chain, we're going to have an electronegative atom. And I'm going to use X just as a generic electronegative atom. I'm going to show examples of oxygens, nitrogens, and halogens to look at these different types of functional groups. The first one I want to do, I'm going to take that X and I'm going to replace that with an OH. This particular grouping of atoms right here gives us the carboxylic acid. The carboxylic acid is one of our basic starting materials, really stable, common functional groups in nature. I can modify the carboxylic acid by, again, just like we've done with our other examples, taking the hydrogen off and replacing it with an alkyl chain. So I still have the oxygen there. I'm going to take off the hydrogen, and I'm going to put an alkyl chain there. Now this could all be represented with R groups. And again, this alkyl chain can be one carbon chains to dozens of carbons. These are called esters. Esters is a carboxylic acid derivative. The carboxylic acid is considered kind of this main functional group, and just by changing the OH group, we're going to see we can end up with a lot of different types of functional groups. I'm going to take this example and I'm going to take off the oxygen now, and let's go ahead and put a halogen. And lots of times halogens are also represented by X, but I'm going to put a chlorine there. This is called an acid chloride. If it was a bromine there, it would react much the same way. It'd be called an acid bromide. You could have fluorines there and iodines there. Very similar structures, very similar reactivities. These are highly reactive molecules that we're going to encounter in second semester organic chemistry. The other atom that we often see replacing the oxygen is a nitrogen. And in this case, I'm going to write two hydrogens attached to this nitrogen. This is called an amide. Now, these amides can also replace hydrogens just like we did with our ester groups. And so we can end up with that nitrogen substituted with same R groups or different R groups. It's still called an amide. It hasn't been changed like carboxylic acids to esters. These are both still amides. This is just substituted amides, where the nitrogen is substituted. Okay, there's one more functional group similar to the amide that is really important that we study. And I'm going to take the carbonyl off. So I'm just going to go through and put a carbon up here with a nitrogen group. These are our amines. There's no carbonyl here. They're a little different than the amides. These are very similar actually to alcohols. They have very much same properties, can act as both acids and bases. There can be they have hydrogen bonding, minimal hydrogen bonding. Nitrogen's not real great at hydrogen bonding, but still makes a fairly good intermolecular bond. The hydrogens can also be replaced here. And so we can have nitrogen atoms that have more than one alkyl group to them. They can be the same alkyl group like I just drew. This is triethylamine. These alkyl groups can also be different. If there's 3 carbon groups attached to it, we say it's tertiary. If there's only 1 carbon attached to the nitrogen, we call it primary. And if we were to draw a structure with 2 carbons attached to the nitrogen, we would say it was secondary. Between our alcohols and ethers, ketones and aldehydes, carboxylic acids, esters, acid halides, amides, and amines, if you can become comfortable with drawing these types of patterns, that's going to cover almost 95% of the molecules we see in organic chemistry.